right, questions 15 and 16 go together, so I will draw them both on here. So first one asks you to recognize oxidized versus reduced forms of a quinone. All right, so quinones basically have this structure where they have an aromatic ring that's attached to hydroxyl groups, or in a different form, it can look like this. Right now, they can have other groups dependent on the sides of them, and they often do. But these are the basic structures of a quinone here. Now, the form on the left, and the key thing here are these hydrogens. Right? Anytime we're gaining bonds to hydrogen, right, we're talking about a reduction. So this is the reduced form. The form on the right is the oxidized form of a quinone. All right, so that's it for number 15. On number 16, draw the Q cycle. All right, so Q cycle starts off with the reduced form of a quinone. We'll draw it as QH2. Now, the key thing for the Q cycle is there are two different paths that, so quinones contain, when they're fully reduced, like QH2, they contain 2 electrons that they can donate. Now, one of these electrons will go on and be donated to through complex 3 to cytochrome C, and then on to complex 4. All right, but the other electron will be donated to a second binding site for Q. All right, and so when that electron is donated to, when this electron donation happens here, the initial QH2 falls out and becomes Q plus 2 protons. Right, these protons then contribute to the proton gradient. Now, one of the electrons went on down the pathway there. We don't care about that one anymore. But one electron went over to the second binding site for Q, turning it into a Q negatively charged radical. Now, in the second round of the Q cycle, another QH2 will come in and bind to this first site. All right, it again will get converted into, it will lose its electrons, becoming a Q and 2 protons. One electron goes further on down the electron transport chain, and the other electron goes to this Q radical, which the Q radical now becomes a QH2, and that can now leave that second binding site. Now, the entirety of this Q cycle now is that we took 2 QH2s and donated their electrons on to other things. But as our products here, the 2 initial QH2s became 2 Qs and 4 protons. But we also got this additional QH2 at the second site. Now, since we have QH2 on both the products and reactants, we can eliminate one of them. And so the net reaction of the Q cycle is actually what's shown here, where one QH2 totally missing something here. Anyways, yeah, there we go. All right, so basically now the net reaction here that we get out of this is that one QH2 gets turned into a Q plus these 4 protons that are given off. Oh, I know why. Yeah, all right, sorry, I forgot about there's another Q as a reactant. That's why the second. All right, let me go back to this part. All right, now I was getting a little hung up on why I was needing to get rid of a Q that I didn't have on here. So if I wrote everything out, all right, for reactants, we had 2 QH2s that bound to the first site, but then we had this additional Q that had to bind to the second site. Now, on the products, we had the two QH2s that bound to the first site both got turned into Qs, and the Q that bound to the second site got turned into this QH2. So now we have some things that are the same on the left and the right, so we can cancel them out. So this QH2, there's a QH2 on both sides, that goes away. There's also a Q on both sides, so one of the ones goes away like that. And we're basically left with this equation here, where when a QH2, a single round of the Q cycle here, will transfer 2 electrons on down the pathway. So 2 electrons to complex 3. And the QH2 will become a Q, but these 4 protons here will be donated and pumped into the intermembrane space of the mitochondria.